Hey everyone, and welcome to This Explainer. Today we're looking at something incredibly cool, the exact roadmap used to train and certify the next generation of technical designers, literally turning raw ideas into globally standardized, manufacturable reality. So, we are diving straight into the official RQFL Level 4 Trainees Manual for SolidWorks Design. Actually, this isn't just theory. This is the foundational module used to certify professionals in manufacturing technology. It gives us a clear, unfiltered look at the industry-standard progression for mastering mechanical design.
And this curriculum represents a seriously powerful collaboration between the Rwandan TVET board and KICA. It really highlights a massive global push to standardize technical education and equip trainees in emerging markets with world-class manufacturing standards.
Okay, before we get to the heavy lifting, let's establish our baseline. This manual focuses heavily on parametric CAD, meaning every single dimension, sketch, and relationship is mathematically linked. It's not just drawing, it's building a highly flexible mathematical database.
Our roadmap for today covers 4 key learning outcomes. 1. Set up workspace. 2. Create parts. 3. Assemble components. And 4. Produce drawing.
Section 1. Set up workspace. Preparing your digital bench.
Think of this first step as preparing your digital workbench before you even pick up a tool. A focused learner knows that setup is all about strict standardization. Selecting the proper template isn't just a personal preference. It actually bakes in your ISO or ANSI drafting standards and your precise units of measurement right from the very first click. This is absolutely crucial for ensuring downstream compatibility with global manufacturers later on.
Section 2. Create parts. Bringing ideas to life.
All right, so with our digital bench perfectly organized, we transition to drafting actual, tangible geometry. The curriculum outlines a very strict chronological workflow here. You always start with a 2D plane, draw a dimensionally constrained sketch, and then apply features like extrusions or revolves to push that sketch into 3D space. Basically, the sketch drives the solid.
Now, this shift from 2D to 3D, it is absolutely critical. In parametric design, your 2D sketch isn't just left behind. It acts as the permanent DNA of the 3D object. If you ever need to change the size of the 3D part later, you just go back and alter that fundamental 2D sketch, which then instantly updates the whole 3D model. Pretty smart, right?
Then, finalizing the component involves assigning actual material properties, like, say, aluminum or steel. This way, the software can calculate precise mass, center of gravity, and structural integrity. Exporting it properly then ensures your file management remains completely clean for the upcoming assembly phase.
Section 3. Assemble components. Building the machine.
Sure, a single gear or bracket is great, but modern manufacturing is all about complex systems. This curriculum teaches the classic bottom-up assembly approach. You import your standalone components into a master file, effectively laying all your digital parts out on the table before applying the mathematical constraints needed to lock them together and exporting the final system.
Because mates are the absolute linchpin of assembly design. Instead of just placing parts visually, you are actively removing degrees of freedom. By applying concentric mates to a cylinder in a hole, or coincident mates to 2 flat faces, you dictate the exact mechanical behavior. You're building a functional, kinematic system, not just a static 3D picture.
Section 4. Produce drawing. The final blueprint. Because out in the real manufacturing world, you can't just hand a machinist a 3D file and say, hey, build this. You need standard blueprints. But the true power of this curriculum lies in associativity. When you import your front, top, and side views onto the sheet layout, those views are perfectly linked to the 3D assembly. So if the engineering team updates a part in 3D tomorrow, these 2D drawings update automatically. It virtually eliminates version control errors. A real game changer.
Now, polishing this blueprint requires meticulous attention to manufacturing reality. We're talking about applying precise geometric dimensioning and tolerancing, or GD&T, and surface finish notes. The exported drawing has to leave zero ambiguity for the machinists down on the factory floor.
The manual also covers modern exporting methods like the 3D PDF. And this is huge. It represents the industry's shift toward model-based definition, allowing manufacturers to literally rotate and interact with the part directly on a tablet. It moves us so much closer to a completely paperless, hyper-efficient factory floor.
And just like that, we've reached the end of the Gen CD41 curriculum.
From configuring a standardized workspace all the way to parametric modeling, kinematic assemblies, and associative drafting, this is the definitive roadmap for modern mechanical design. So, armed with the structured skills to turn concepts into reality, what will you build next? Thanks so much for joining me on this explainer.